Now we have a short section, solutions of triangular systems. Let's begin with definition for triangular matrices. A square matrix L is lower triangular if the entry is 0 when I is smaller than j, which means that for the given matrix and from along with diagonal below, these are not possibly non-zero entry, but a proportion is 0, then it is called the lower triangular. And opposite way, for a square matrix, including diagonal and a proportion is possibly non-zero and below is 0, then it's called upper triangular. G is a triangular matrix, then G is non-singular if and only if diagonal entries are non-zero, all of them. All of these diagonal entries are non-zero, then it is invertible. Okay. Now let's try to solve lower triangular systems. Okay, we start with Ly equals B. L is a non-singular lower triangular matrix. And to solve this system, we try to write it in detail. So once this lower triangular matrix Y multiplied, then we have the first row and L11, Y1, and right hand side is P1. From second row, we have this line, and so on. That is from the last row. The goal is to find Y. So that from the first equation, we divide this equation by L11, then we can get Y1, right? So we can get Y1, and then once Y1 is known, then we move this one to this side, the other side, and then divide by L2 to get Y2. We can keep going. Now at this point, Y1, Y2 are known, so that again, we move these known terms to the right side and divide by L33, and we can get Y3. Okay, we can go up to the end. Okay, that's the algorithm. So here, in general, once we have y1 to yi minus 1, then we can solve for yi using the ith equation. So known moved to the right side and divided by Lii, that is yi. We can implement this quite easily in MathTalent. Here the input and bi is now, we are using the same array and the subtracted and then divide by Lii. So output, in output bi is the solution y. Okay. You can implement this the further substitution along with some factorized form, but here I implemented that in detail, pointwisely. Now, what is the computational complexity? For each I, the further substitution requires 2 I minus 1 plus 1 flops. Flop is a floating point operation by any of these one. Earlier in the history of computational mathematics, only multiplication and division are counted. But nowadays we count every operation as one flop. It means that, and earlier in computation, multiplication and division is way more expensive than an addition and subtraction. But in modern computers, of course, multiplication and division are more expensive, but now counting every operation is more reasonable due to the very advanced technique for multiplication and division. Okay, for each I, we need two I minus 1 plus 1 operations. Look at here. For this one, just one division is okay. Now, for that one, we multiply 1 and here subtract, and then one division. Okay. So here, that one is division, and that is now multiplication and subtraction the other side. Okay. We can simplify to get n squared. It requires n squared operation. Now let's go to upper triangular systems. Okay, again, we'll use the exactly same strategy, writing it in detail. And ux equals y. Then we have these lines. Now here the target is to get x. So by using from this last line, and divide by unn, we can get xn. Once xn is determined, then we can move this to the other side and divide by this quantity, and so on. So that in backward way, we can decide x values. That is exactly the back substitution. And this is a little bit different implementation strategy, but you can check this one is okay. For this back substitution, the computational complexity is n squared with a small portion and of n. So eventually, the number of required operation is n squared. Okay. Now here, this for the elimination and back substitution is a sort of optimal. The computational cost is minimum. It cannot be smaller than this cost. For example, now for lower triangular system, okay, we have the maximum possible number of entries n plus 1 over 2. So that it is like almost n squared over 2. The entry is here. When we try to solve the problem Ly equal b, here for each one, you have to apply either multiplication or division, and then addition or subtraction. So that for each entry, you need two operations. So there are n squared over 2 the entries, so that here number of flop must be order n squared. It cannot be smaller than that. Okay. Also, for the upper triangular system, we can claim the same is a kind of optimal algorithm. Okay. That's the end of the section. Thank you.